Welcome to Messy Math Moments Matter, where we explore experiences to help students engage in math more deeply. When we allow opportunities for math to get a little messy, we will see big results. Don't worry about it being perfect. Math class should be perfectly imperfect, just like this video. Today we're going to be exploring grade 6, organizing idea number, learner outcome number 3, students analyze numbers using prime factorization and exponentiation. So what I've done is I've gone ahead and I've highlighted the cusp that I will be deliberately focusing on in these experiences today. For understandings, a product can be composed in multiple ways, and the prime factors of a number provide a picture of its divisibility. These are the knowledge pieces that students need to know, and the skills and procedures, the things that students will need to do in order to build these understandings that work their way up to this learner outcome. So why this experience? Well, this is going to build upon students' previous experiences with multiplication and relational rods in order to explore prime factorization. The materials you will need are relational rods. Students will need to have prior experiences using those. And there is a Google slideshow that you can use called Prime Factorization with Relational Rods. So the first experience will be using base 10 blocks in order to multiply two-digit numbers. Now, if students haven't done this, you might want to skip this particular prior experience, but it is my favorite way of teaching students how to multiply two-digit numbers. So if you want to check that out, you'll be able to find that in the grade 5 long-range planning documents. So normally students would have a piece of paper or whiteboard on their desk. So I'm just going to use this piece of paper to help me distinguish it between my paper and the desk. And if students were multiplying 11 multiplied by 12, they would build 11 on the outside, and 12 on the outside. Then they would find a base 10 block that fits right here that has an area of 10 multiplied by 10. A base 10 block that fits right in here that has an area of 10 multiplied by 1. A base 10 block that fits in here that is 1 multiplied by 10. A base 10 block that fits right in here that is 1 multiplied by 10. A base 10 block that fits right in here that is 1 multiplied by 1. And a base 10 block that fits right here that has 1 multiplied by 1. And when they're done, they'll be able to see that 11 multiplied by 12 is 132. Now, the reason we want to connect back to this is that we want students to be able to see the factors or the dimensions of this will create this particular array, and I can use that to help myself figure out what my division was as well. So the next experience I will use in order to help students connect back to prior experiences is using the relational rods to explore single-digit multiplication. So if I was looking at 6 sevens, I could build my 6 here and my 7 here, and then I can show 6 sevens. There's 1, there's 2, and then I can just keep filling this up until I have 6 sevens. I can see my 6, I can see my 7, and I can figure out that that is 42. And then, of course, I can use the commutative property. So if I wanted to, I could switch these around, 7 sixes, and then show 1 6, 2 6, 3 6, and so on, and then I can add those up. Again, I'm more unitizing the 7 here and the 6 there to show what that array would look like. The third experience that I would use for students to explore their background knowledge would be to give them something like this one. And I would ask, what division statement does this represent? So they could say, well, there's 10 altogether, and I've divided it into fives. So that would be 10 divided by 5 is equal to 2. Or they might say, I have 10s and I have them divided into 2 equal pieces. 10 divided by 2 is equal to 5. Either one of those statements is correct for this representation. But I've activated their background knowledge. Let's go ahead and jump into the actual experience. So I would ask students to create as many arrays as they can that have a total value or a total area of 12. So students might start by building 6 twos, or they might build 2 sixes, or they might build 3 fours, or 4 threes. Sometimes that's where students will end. They might not right away catch the last two, which include 112 and 12 ones. So regardless of how many they found, whether they found those two or not, I would ask the question, how confident are you that you found them all? Are there any more you didn't find? And let students play with that for a little bit. So once they've done that, and I've had them share back and I've displayed these on the board, then I will ask them to help me figure out what the dimensions of these arrays are. So in this case, this is a 6 by 2. There are 6 twos. The dimensions is 6 by 2. The factors are 6 and 2. This one is 2 sixes. So dimensions would be 2 by 6. Factors 2 and 6. 4 by 3. 4 and 3. 3 by 4. 3 and 4. 1 by 12. 1 and 12. 12 by 1. 12 and 1. So we're going to consider this array. I'll just move this one out for now. And I would like students to figure out what the dimensions are again. And they already told me it was 6 twos. So I'm going to go ahead and put those factors, put those dimensions on my table using my relational rods. So here are my 2's. And here's my 6. Now, here's a new rule just for now. I can only build on my table the dimensions, the factors, using prime numbers. So I might have to do some replacement here. Let's take a look at the 2. Well, they might say, well, I could replace that with 1s. And that would give us an opportunity to talk about, is the number 1 prime? Is it composite? Is it neither? To reinforce the fact that 1 is neither prime nor composite, so I can't use 1s. So 2 is a prime number. That one's fine. What about 6? Well, 6 is not prime. So what could we do to replace the 6? Well, I could replace it with 3 2's. 1 2, 2 2's, 3 2's. Well, how would I represent that? Well, I had 6 multiplied by 2, and I replaced the 6 with 3 2's multiplied by 2. Now, there's something that you need to know. Number 1, I can rewrite this as this. But the other thing you need to know is that mathematicians tend to like to organize things in a logical way. If it's letters, they'll organize it alphabetically. If it's numbers, they prefer to organize it in number order. In this case, I can do that. So 2 multiplied by 2 multiplied by 3. But what if they didn't replace it with 3 2's? What if they replaced it with 2 3's? There's 1 3, 2 3's. So that's 6 by 2. They replaced this with 2 3's. And then multiplied by 2. So I can rewrite that as 2 multiplied by 3 multiplied by 2. But again, a mathematician would organize this because changing the order we know won't change the result when I multiply it. What do I notice? Well, I notice that I ended up with 2 multiplied by 2 multiplied by 3 when I replaced it with 3 2's. And I ended up with 2 multiplied by 2 multiplied by 3 when I replaced it with 2 3's. So it didn't matter which way I replaced it, it still ended up with the same factors, and they are all prime numbers. So we have a fancy name for that. Prime numbers that are the factors are called prime factors. Now we'll go ahead and we'll replace that process. We'll repeat that process for this answer. So just to make this a little bit easier to see, I'll go ahead and trace this line here. Not that you need students to do that because they can build it up here. So what would be my factors? Well, this would be a 4, and this one would be a 3. So this would be 4 multiplied by 3, but 3 is a prime factor, but 4 is not. That's a composite factor. So what could I replace 4 with? Keeping in mind I have to use the same color. Well, I could replace 4 with 2 2's. Now the nice thing, a neat little trick would be to use a red marker when I'm writing down the 3 and a blue marker when I'm writing down the 2's. Just to help students see that color change. I'm just using black for now. So the 4 became 2 2's multiplied by 3. So I can write that as 2 multiplied by 2 multiplied by 3, and it's already in the correct order. Are there any other options for replacing the 4? No, because the only other option is 1's, and we know 1's are not prime numbers, so that's actually not an option. Let's go ahead and do this one. So I will just trace that to make it a bit easier to see. Well, this would be 3. This would be 4. So I have 4 multiplied by 3 here. The 3 is a prime number, but the 4 is not. And students might already be able to see a pattern here. So my 4 becomes 2 2's multiplied by 3. So 2 multiplied by 2 multiplied by 3. And I'm down to just my prime factors. Okay, let's take this one here. I have my 2 6's. I can see a 2 would go here. A 6 would go here as my factors. And now I need to figure out my prime factors. My 2 is fine. My 6 has a couple different options. I could put 2 3's, which would give me 2 multiplied by 2 multiplied by 3, or I could replace that with 3 2's. So there's my 2 multiplied by my 3 2's, 2 multiplied by 3 multiplied by 2. Let's put that in order. Interesting. So I'm going to stop there for a moment, and let's take a look at what we built and what do you notice about the relationships? What patterns do you see? Well, students should see that every time, no matter which way they built it, they ended up with 2 multiplied by 2 multiplied by 3. So it didn't matter if they built their array as a 6 by 2 or a 2 by 6 or a 4 by 3 or a 3 by 4. You might be wondering about this one. Let me just move this off. There we go. Well, what's the trouble with that one? Well, yes, I could build 12 up here, but this factor is 1, and 1 is neither prime nor composite. So we can't actually replace that with a prime or composite factor. So we would never use this one in order to figure that out. What about the one where I built it with 12 ones? You probably already figured out I'm going to run that exact same problem. I can do 12 up here, but I can't have 1 as a factor here using the special rules because 1 is neither prime nor composite. We would never start with the array that has 1 as a factor in order to find the prime factors of a number. I would always start with an array that has something other than 1 as one of the factors. So when we built all of these arrays of 12 and we found all of the prime factors of those arrays, so we found the factors of each one and then we turned them all into prime factors, we actually found the prime factorization, just a big fancy word for finding the factors but only using prime numbers for it. And when we did that, we found that they were always the same no matter which way we built the array. So the prime factorization of 12 will always be 2 multiplied by 2 multiplied by 3. So the factors that are only prime numbers would fit that way. So your turn will be to find the prime factorization of 18. So when I do prime factorization for 18, I know I can build any of the arrays for 18. So I'm going to build 2 9s. So I can build them like this, or I can turn them like this. It doesn't matter which way that I build this. So for my 2 9s, there's my 2. I know that one's a prime number. Now I don't have any extra 9s here, but I already know that that's a composite number. So I can go ahead and replace this with something else. So I'm going to take my 3s because I know 3 3s make 9. 3 3s are equivalent to 9. And now I have my prime factorization. So I could just remove this to get this out of my way so I can see this a bit better. And then I'll just put this in numerical order from smallest to largest. 2 multiplied by 3 multiplied by 3 multiplied by 3. This time let's find the prime factorization of 20. So a student might build 20 as 5 fours. And they would say, well, it'd be 5 by 4. So just to make life simpler, I'm just going to remove these so it doesn't get mixed up in my answer because it's hard to distinguish. So there's my 5 and there's my 4s. Well, my 5 is prime already. My 4s I could replace with 2 2s. So it'd be 2 multiplied by 2 multiplied by 5. And I can double check to make sure that works. 2 multiplied by 2 is 4. 4 multiplied by 5 is 20. Now let's represent that mathematically because we're not always going to have the relational rods to help us figure this out. It's a great way for us to visualize it. I could draw pictures of it, but a mathematician always looks for opportunities to represent this with numbers. So let's start back from the beginning. So I built 20 as 5 fours. So here's my array of 20, and I built that as a 5 by a 4. My 5 was a prime number, so I can just circle that to help me remember that it was prime. But my 4, I actually replaced with 2 2s. And my 2 is a prime, and my 2 is a prime. So the prime factorization of 20 is 2 multiplied by 2 multiplied by 5. Now let's say my first array was 2 10s instead. Well, I know that this would be a 2 multiplied by a 10. So just remove this out of the way so I don't lose track of it. So here's my 20. that I started with, and I did a 2 by a 10. This time I'm not going to draw the array boxes. I know that my 2 is prime, so I'll circle it. My 10, though, I could have replaced with 5 2s. 1, 2, 3, 4, 5. So my 10 I replaced with 5 2s. Well, that's prime. So 5 2s. So now I could say this is 2 multiplied by 2 multiplied by 5. And I ended up with the exact same result. So that's a great way for you to double check that you've found the correct prime factorization by looking at it from a different perspective, building a different array in order to do that. Go ahead and find the prime factorization for 16. Well, what I can do is I'm going to imagine that I've built an array of 16. Let's say I do that array of 16 with 4 4s. Well, this 4 can be replaced with 2 2s, which is prime. And this 4 could also be replaced with 2 2s. So this would be 2 multiplied by 2 multiplied by 2 multiplied by 2. I might want to double check that though. So let's try it a different way. And say I either built it with 2 8s or 8 2s. This one's prime. But my 8, I could replace that with 2 4s or 4 2s. So let's say I replace it with 2 4s. Well, this one's prime. This one's not. 2 and 2. So I get 2 multiplied by 2 multiplied by 2 multiplied by 2. Again, it matches up. So now I know that I'm good to go. So here's a challenge one for you. Try the number 30. So I would have two choices. I could build my 30 as an array and then work my way through that and then represent it using this format. Or I could use this format to represent it and then build it a different way to check. So let's take a look. Maybe I built it with 6 5s. Well, my 5 is prime, but my 6 is not. So my 6, I could build that with 2 3s. And both of those are prime numbers. So my prime factorization would be 2 multiplied by 3 multiplied by 5. And I'm going to double check to make sure I did that right. 2 multiplied by 3 is 6. 6 multiplied by 5 is 30. Now this is called a factor tree because it has so many little branches in it. So it's a model we can use to model the way that we built it using the relational rods. You were creating a factor tree of some number, but we don't know what it was. What you do know to be true is that when you were done, the prime factorization was 2 multiplied by 2 multiplied by 3 multiplied by 5. Can you figure out what that original number was? Go ahead and create a factor tree that would allow you to demonstrate the factorization of whatever number you built. So there's a couple of different ways you could do this. You could say, well, I'm going to look at it like this. I have 2 2s and 3 5s. So I could build 2 2s and represent 3 5s as well. And I could fill it in and figure out what that one looks like. Another option, if I want to jump right to this, would be that the 2 2s would come from 4, the 3 5s would come from 15, and then 4 multiplied by 15 would be 60. Another option I could do is 2 multiplied by 2 is 4, multiplied by 3 is 12, multiplied by 5 is 60. So there's a couple different ways that I could do that if I wanted to. I might also say, you know what, I don't like the way these numbers are written. We know it was put in numerical order when it was done, but maybe there's an easier way to figure it out. What if I put the 2 and the 5 together and the 2 and the 3 together? So the 2 by 5 would give me 10. The 2 multiplied by 3 would give me 6. And the 10 multiplied by 6 would give me 60. So many different options in order to help me make this a little bit easier to figure out. Let's also do the number 42. So go ahead and create your tree for 42. Again, you could build the array first and then check with your factor tree, or you can draw it using your factor tree and then build it to check. So 42, I might not remember what goes really well in there, but I do know that 2 will work. It'll always be 2 of something. How do I know that? Because it's even. 2 of what? Oh, 2 of 21 will work. So 21, oh, that's not prime. So let's put a box around it to remind myself it's not prime. Sometimes that happens where you think it's prime and then you remember that you can actually create 21 with 3 7s or 7 3s. Well, 3 is prime, 7 is prime. So 42 is 2 multiplied by 3 multiplied by 7. So let's focus just on 30 and 42. So the prime factorization of 30 and the prime factorization of 42. What do you notice that's the same, similar, and different? Well, I notice that they both have a factor of 2 in it. So maybe I'll put a little star here. That means 30 is divisible by 2, 42 is divisible by 2. What else do they have in common? Well, they also both have 3 as a factor. So we'll put a star beside the 3 there and there. Well, what's different? Well, the 5 is a factor of 30 and 7 is a factor of 42. 5 is not a factor of 42. 7 is not a factor of 30. 30 is divisible by 5. 30 is not divisible by 7. 42 is divisible by 7. It is not divisible by 5. So the common factors between 30 is 2 and 3. There's another one. There's another hidden factor in here. It's a little bit more obvious in the 30 than it is in the 40. Can you find another number that both 30 and 42 are divisible by? Well, that's 6. It's really obvious right here because you can see the 6. But I didn't split up 42. I didn't factor 42 in such a way that the 6 is obvious. Can you see the 6 in here? I can see the 6 right here. 2 multiplied by 3. It's a lot more obvious here. So both of these are divisible by 2, 3, and 6. And I used the prime factors that I circled here to help me find the 6 here. What is the largest factor that both of these have in common? So 6 isn't a prime factor, but I didn't ask which was the largest prime factor. I asked which was the largest factor. So the largest factor that they have in common is 6. So we call that the greatest, which is another word for largest, common factor. Now, in some areas, people will call it largest common factor, so you want to be prepared for both. Often we'll be lazy, and we will call this the GCF, greatest common factor. And if you're using largest, it would be LCF. But for the most part, we use greatest there. So this time, let's find the greatest common factor between 16 and 42. I already have them built here, so I don't need to redo that again. But I want to look for the greatest common factor. So let's see what they have in common. Well, it has a 2 and a 2 in common, so there's a 2. This 2, oh, I already used up that 2. I can't use it again. So there's no other 2. 2, no, there's no other 2. 2, nope, there's no other 2. So there's only one factor they have in common, and that's the number 2. So let's create a factor tree for 24. Maybe I figured it out doing 2 multiplied by 12. 12 would be 2 multiplied by 6. And 6 would be 3 multiplied by 2. So my prime factorization is 2 multiplied by 2 multiplied by 2 multiplied by 3. Now there are other ways I could have built 24. When I look at my prime factorization from here, can I figure out what those other ways were? Go ahead and give that a try. Well, I could have done 4 multiplied by 6. So there's some more factors. I could have done 3 multiplied by 8. So I can use these prime factors to figure out all possible factors of 24. So I've got 2 will divide into 24, 3 will divide into 24, 4 will divide into 24, 6 will divide into 24, and 8 will divide into 24. A factor tree will give you an opportunity to figure out all of the possible factors of 24. So let's go ahead and see if we can figure out what that would be for 96. So I'm going to show you one factorization of 96 here. So 2 multiplied by 48, 6 multiplied by 8, 2 multiplied by 3, 2 multiplied by 4, oops, and 2 multiplied by 2. All right, so 2 by 2 by 3 by 2 by 2 by 2. There's a lot of them in there. Well, I know 2 will be 1. 3 will be 1. And I can see here that 4, 6, and 8 and 48 will be 1. And of course, 1 and 96 would be factors. But did I miss any? Let's see if I can find any kind of hidden in here. So we have 2 multiplied by 2 is 4. Yep. 2 by 3. Yep. 2 by 4 is 8. Yeah. Let's try 2 multiplied by 2 is 4 by 3. Oh, that's 12. So let's put 12 in here. And I won't worry about it being out of order right now. Well, 12 multiplied by what will give me 96? Well, if these multiply to 12, then these must be what I need to get to 96. Two multiplied by 2 multiplied by 2, which is 8. Oh, I already have that one. Okay. What else? 2 multiplied by 2 multiplied by 2 multiplied by 2, so 16. So I'd use that one, that one, that one, that one. And you might be thinking, oh, I'm starting to lose track of which ones I've used. So it actually might be really helpful to take 1, 2, a 3, a 2, a 2, and a 2. There's my prime factorization. So then I could say, well, I built 16 this way. 2, 4, 8, 16. Because remember, I'm multiplying these together. So that leaves me 3 multiplied by 2, which is 6. Oh, I already have that one. Okay, so then I can just throw in, do some exchanges. 2 multiplied by 2 is 4. Multiplied by 2 is 8. Multiplied by 3 is 24. Oh, I don't have that one. And multiplied by 4, which I already have. If I'm not sure if I have most of them, I might try reorganizing this. So 1 multiplied by 96, yeah. Or 2 multiplied by 48, okay. There's my 2 multiplied by 48. 3, what would I multiply 3 by? Well, it'd be all of this. 32. Oh, I missed that one. So I'll write that one down. 4 multiplied by 24. 5. Well, I know 5's not going to work, but I checked it just in case. 6 multiplied by, that's by 8. So 16. I have that one. 8. You can see 8 would be multiplied by 12. I have that one. Oh, I didn't check 7. So I could do some math. Nope, that one won't work. Okay, so 8 I did. Let's check 9. No, 9 won't work. 10, no. 11, no. So there we go. I found all of the factors. There was a lot of them, but it's a nice way to test by choosing one as the one dimension and then finding the other dimension of your array. So if I had 96 and one of the dimensions was 2, I could figure out that 48 would have to be the other one. So that was it for this experience. Hopefully you found that helpful. If you have any ideas for future Messy Math Moments Matter videos, please don't be shy about sharing that with me. Hopefully we'll see you in the next one.